Calculating moment of inertia, let me remind you, for a single particle over here, the moment of inertia of this one particle, distance r from the, let's assume the rotation axis is the z-axis coming out of the page, then the moment of inertia of a single particle is its mass times its distance from the origin squared, and that r squared came from converting angular velocity or regular velocity to angular velocity. If we have many particles, so let's say we have a hoop, like in the video you just watched, then to get the, and let's assume the radius of the hoop is big R, and that its total mass, oops, not R, its total mass is M, then the way you approach this is you break the hoop up into a bunch of pieces. You calculate the moment of inertia by adding over some index j, the mass of the jth piece times the radius squared of the jth piece. So we're using the single particle moment of inertia formula. And here is the number of pieces you choose to use. So for the hoop, all of the pieces have the same R, and that R is big R, and if we assume, we can assume if we want to then, that the pieces are the same size, so the moment of inertia is big R squared for each one of them times the sum of all of the small pieces of mass, and if you add up all the small pieces of mass, you get the total mass, and so we could write the moment of inertia as mr squared, and I'm going to stick a factor of 1 in front there. Obviously multiplying by 1 doesn't make any difference to the value, but it's useful for something later on. Okay, so let's talk about a solid disk or cylinder, like the ones rolling down the incline in the video. So we imagine doing the same thing. Well, let's step back. So total mass is M, outer radius is R. We're going to imagine breaking the mass up into a bunch of pieces, but now each one of those pieces, and I'm not drawing them the way I would organize this calculation if I was actually going to do it, each one of these three pieces, label them 1, 2, and 3, each one of those pieces have different r sub j squared. So like we did up above, the moment of inertia is the sum over all of the pieces, the mass of each piece times the rj of each piece. It turns out that for a solid hoop, I'm looking up the equation right now, the moment of inertia of a cylinder like this is ½ mr squared. This is not at all obvious. You need to do this right, set it up, do an integral, change the sum into an integral, and then you get the result, 1/2 mr squared. One way to think about why this factor out in front of m r squared is smaller for the solid disk is that for the hoop, everybody's rotating, imagine it rolling, everybody's rotating around at the same speed, and they're all the same distance from the center, and they're all far from the center. In the disk, some of the pieces are close to the center, some are far away from the center, so some will be moving slowly because they're close to the center, some will be moving quickly because they're farther from the center, and so the moment of inertia ends up being smaller for the case of a solid disk or cylinder.